Okay, let's talk about trig functions. Yay, graphing. All right. So we're going to graph two functions on this grid. I'd like to graph sine x and 3 sine x. And we're going to talk about how the 3 affects the graph of sine. So if this is 2 pi, and if this is negative 2 pi, which pi is halfway, where does sine start? You could ask Google if you forgot, or you could ask your unit circle, right? Sine starts at the origin, yes. And by pi halves, what's the sign become? 1. And then by pi, it's at the 0. By 3 pi halves, you're at negative 1. 2 pi, you're back at 0, and that pattern continues in the negative direction as well. Now the important things about this graph are, how long a cycle is, that you get it starting in the right point, that you get the right highest and lowest points. What's that 3 gonna do? It's gonna do something that's called, you don't know what the amplitude is yet, but you're using words these guys don't know yet, but that's okay. So it will take all of the y values and multiply them by 3. Does that make sense? So this y value, that's 0, it stays 0. This y value is 1, what does it become? 3. That y value is 0, it stays 0, right? This y value right here, that's negative 1, multiplies by 3 becomes negative 3. I missed my dot. And do the same thing on the other side. The tallness of that curve, or the deviation from the x-axis, is called the amplitude. And it's defined as half the distance from top to bottom. So how far is it from highest point to lowest point? 6. And half of that is 3. So this number out in front is going to describe what is the amplitude, or the deviation from that center line. So this curve has amplitude 3. And that will describe how tall the curve is in some sense. Does that make sense? Amplitudes that are, so assuming we're talking about positive numbers, amplitudes that are bigger than 1 are going to stretch the graph, right? Amplitudes that are less than 1 are going to compress the graph. If you had a negative number, what's it going to do to the graph? It's going to flip it, and then it will stretch it if you have, ignoring the negative numbers bigger than 1 over the x. Yep, exactly. So like this one, we're going to graph cosine x and 1/2 cosine x. So where does cosine of x start?
0, 1.
At 0, 1, yep. And if this is 2 pi, it crosses at pi halves. By pi, you're at negative 1. 3 pi halves, you're at 0. 2 pi, you're back at 1. They trickle in. Hi. So what's the 1/2 going to do to this cosine picture? It's going to go squish. Yep, so this, instead of crossing at 1, will cross at 1/2, right? The zeros stay in the same place, don't they? So roughly speaking, there's a graph of 1/2 cosine x. What is the amplitude of that graph? 1/2, yep. So takes the y's, multiplies them by 1/2. What would it have been if it was negative 1/2? What would have changed? It would have flipped it. Does that over the x-axis? Okay, so all the same patterns that you know for like what negatives and stuff do to functions, they apply to these functions too. And if you're uncertain and you want to check, it is totally reasonable to use Google to like confirm that you're correct. Does that make sense? Like it's okay as long as you understand why the patterns are true. Okay, so a function y equals a sine bx or a cosine bx, that number a is called the amplitude of the graph. And it describes the maximum deviation from the x-axis, meaning what is the farthest it gets from the x-axis in the up or down direction. So numbers outside, not so tricky. Now this one, we've got sine of x and sine of 2x. This is a bit more tricky, so just start by graphing sine. Yes?
I have an issue with your definition. What if the graph has been like shifted up or down?
That's a great question. That is because they said given an equation a sine bx, and they didn't allow it to be a graph that shifted up or down. If it's a graph that shifted up or down, it's deviation from the line it shifted up or down to. Yeah, because I totally buy what you're saying, because you're like, what if you shift that graph up? Then it's not, but it's because they said it's like that. Yeah. Okay, so graph sine of x. I'll drink coffee while you finish, and we can talk about where to go from there. Okay. Let's pick some numbers to plug into this thing to graph the sine of 2x. Does it make sense that something is going to happen sort of horizontally, but we just aren't quite sure what? Okay. I think my first impression when I first saw this, when I was like your age, is like, oh, it's gonna stretch the graph out. That's kind of what I thought was going to happen. That's not what's going to happen. Okay, so what happens when you plug in 0? You get sine of 0, which is still 0, so you're still there. What's the next number you want to plug in? Pi over 2? Sure. So pi over 2, you get sine of pi, which is also 0. So we have a 0 there. And if you plug in pi, you get sine of 2 pi, which is once again 0, right? Does that make sense? That's what's happening? So then the question is what's happening in between 0 and pi halves and pi halves and pi? Does that make sense? So what would be a number to plug in? What's halfway between 0 and pi halves? Pi fourths. So you plug in, you got sine of 2 times pi fourths, which is, so 2 pi quarters makes pi halves, and sine of pi halves is going to be 1. So when you're at pi quarters, the y is 1. Do you see what? Yes.
Why sine 2 pi equals 0?
Why does sine of 2 pi equal 0? Because on the unit circle, 2 pi corresponds to that point, 1, 0, and sine is the y, so it's 0. Yep. What's the number to plug in that's halfway between pi halves and pi? Nope. If you have a half and a whole, what's half of between the half and the whole? 3/4. Yep, 3 pi quarters. So that's sine of 2 times 3 pi quarters. That was a terrible 4, sorry. Which is sine of what? 3 pi halves, and what's that going to give you? 3 pi halves is down here, right? -1. So look at what happened. Usually the length of a cycle was 2 pi, right? What is it now? 1 pi. And you can see that pattern is just going to continue. So halfway, that'd be 5 pi quarters, you'd be back at 1, down to 0. And then it continues in the negative direction. That's like this. One thing you can think about is that you took the x and multiplied it by 2, which makes it oscillate twice as quickly as it usually does. That's one way. It's actually also the case that if you have something like a sine bx, this number b is the number of cycles in 2 pi. That's always true. Do you see how this between 2 pi, between 0 and 2 pi, how many cycles did my blue picture run through? How many cycles? Like, so how many complete patterns did it run through? See, it ran through 1 complete pattern, right? And then another. So this number that's with the x will tell you how many cycles you're going to run through in 2 pi. Like if it was 3 halves, you'd run through 1.5 cycles. Okay, let's try another one of those. Okay, so if doing 2x sped the oscillations up, what do you think x over 2 is going to do? It's going to slow down. Okay, so let's graph sine of x and then sine x over 2. So it starts at 0, by pi halves, you're up at 1, by pi, you're down at 0, 3 pi halves, we're at -1, 2 pi, you're back at 0. Okay, so when you're at 0, when you plug 0 into x over 2, what do you get? 0. So that becomes sine of 0, which is still 0, right? But now when you put in pi halves, you have sine of pi halves over 2. What is pi halves divided in half? Pi fourths. And sine of pi fourths, that's this middle one right here, right? Root 2 over 2. And you do not have to have this memorized. That's approximately 0.7. So when you're at pi halves, instead of being at 1, you're at like 0.7-ish. what happens when you plug in pi? You get sine of pi over 2, which is 1. So by pi, you're up at 1. This one's going to go back down. What's the next nice number when you plug in 2 pi? You get sine of 2 pi over 2, which is sine of pi. That means you're at this angle. And what is the sine at that angle? 0. So how many or how much of an oscillation did that sine function go through? It wasn't even a whole oscillation, was it? It was just half of one. Remember I said that the number with the x is how many oscillations you go through? Can you all see that the pattern is just going to continue in the negative direction? So it will not be until, see this is pi, you were at positive 1. At negative pi, your picture will be at negative 1. And then by negative 2 pi, you'll be back at 0. And I think this kind of holds with the pattern of stuff that we've discussed. So like when you first saw y equals x plus 3 squared, you really thought that that parabola is going to move to the right 3, didn't you? I thought that, right? But what happens to the parabola in reality? It moves left 3. It's the opposite of what you expect, right? And with this stuff, when you got numbers inside, when I first saw sine of 2x, I thought, oh man, that must like make it take twice as long, but it's not the case, right? It's the opposite of what you expect in both cases. So, but it's pretty easy to convince yourself that your first intuition is wrong by just plotting points. Okay, so here we go. So to find that period or length of a cycle, what you can do is this. You can take this thing inside, that bx, and you can set that equal to 2 pi. And if you then solve that for x, it will tell you how long it takes your picture to go through one cycle. So for example, the curve that we had, the first one was sine of 2x, right? If I took this 2x and I set it equal to 2 pi, whenever 2x equals 2 pi, for whatever x it is, it tells me how long it'll take me to finish a cycle. And if I solve that for x, what do you get? X equals pi. And didn't our first cycle in that picture actually end at pi? It went like boop, 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 right? The other one was sine of x over 2, right? You take that x over 2 and set it equal to 2 pi. What do you get? 4 pi. And the picture that we drew, we only drew it to 2 pi, but you'd only done half of the cycle, right? So to get the rest of it in that direction, you would have had to go all the way over to 4 pi. Okay, so let's do that for this one. So just find the amplitude and, if applicable, the period of the function. This will apply, we will not be finding a period of a function if we're talking, the amplitude won't apply for certain kinds of trig functions like tangent, because they have infinite height. So what is the amplitude for this first one? 1/4. And to find the period, you set x equal to 2 pi and solve for x. Well, that first one's done, right? The basic length of a cycle for cosine and sine without anything with the x is 2 pi. Okay. How did you find which part? The period you always find by taking this thing and setting it equal to 2 pi. And the basic cosine and sine functions that have no number in there with the x, they always take 2 pi to go through a cycle. Tangent and some other ones are a little bit different, but sine and cosine take 2 pi. This one, even though that's a negative number, the amplitude is always a positive number. So the amplitude refers to the deviation from the x-axis. In this case, it is 2. What that negative means is if you were to start graphing, your graph is going to initially go down as opposed to up. To find the period, you say, okay, well, when is 2x equal to 2 pi? Because when that happens, I'll have made it through one cycle. Can you solve that for x?
Yes.
Yes, what will it be?
Pi.
Pi. So I'll take pi to go through one cycle.
You just set whatever's in the parentheses.
You set that stuff that's being signed or cosigned into 2 pi. It'll be different if it's a different trig function. Okay, so I'm being a little bit careful with it. So for sine and cosine, it is indeed 2 pi, but for tangent and cotangent, it's pi over, it's pi, I believe. So it's a little bit different for those. What is the amplitude for this next one?
17.
And to find the period, you set pi. I have an extra x there, guys, so please scribble one of them out. It's a typo. Whoops. You set pi over 2x equal to 2 pi. So first multiply the 2 over, and you get pi x equals 4 pi. Divide by pi, and what will x be? 4.
So it would be 4, 4.
Just 4, like no pi's at all, like as in like the regular number 4.
Oh, no, I mean on the graph.
Yeah, we're gonna graph one of them. Yep, so if you were gonna graph one of them, like at 4 would be when one of your cycles ended.
Oh, okay.
And so like, halfway would be 2 and there'd be 1 and 3. And since it was negative, it would start off at negative 17. It'd go up, cross at 1. By 2 it'd be at positive 17. It'd cross and go back down. It's just that the divisions on the x-axis are different because of the stretching. Yeah, we'll graph a few of them, so like this one. So 2 sine 4x, and I said the interval from negative pi to pi, so I'm going to call this pi, I'm going to call that negative pi. Will this function oscillate more quickly or more slowly than a basic sine function? More quickly, yep. Okay, so first thing, find the amplitude. It's 2. Then next thing, find the period by setting 4x equal to 2 pi. So x would equal 2 pi over 4, which is pi over 2. So if this is pi, if those tick marks are 1, 2, 3, 4, which one is pi over 2? The second one, there's pi over 2. And what the period being pi halves means is it means that you've gone through that whole sine pattern by pi halves. Okay, so where does sine start? Usually. Starts at 0, and it usually also ends at 0, right? And it's 0 halfway in between, yes? If you think of like the basic picture of sine, the basic picture of sine does this kind of thing, right? The question just is where are those cross points? And so if your period is pi halves, that's your ending point. You're 0 at your end, you're 0 at your beginning, and you're 0 halfway in the middle. If your sine is positive, what happens as you leave the x-axis? Do you go up or down? Up. And so if this is pi over 4, what's halfway there? It's going to be pi eighths, right? But the point is you're going to go up to 2 at that point. So you go up, down. What happens halfway between pi quarters and pi halves? And what number are you at that point? Negative 2. Do you see how it's sort of the same basic picture as a regular sine function? It's just that the endpoints of it are different. Okay, so then do it again. So you have those 0, 0, 0. Halfway between the zeros you go up, halfway between the next zeros you go down. If I would have asked you to graph to 2 pi, how many cycles would you have in 2 pi?
8.
If I had gone from negative 2 pi to 2 pi, yeah, it would have been 8. Does that make sense? There are 4 of them from 0 to 2 pi. Negative pi halves, and just go backwards, same pattern. First you go down, then you go up. Personally, I have to draw the 5 points every time to really just make sure that I get them in the right spot.
So you just started at 0.
Sine, unless it's been shifted up, always starts at 0. And that's because of the unit circle definition.
Oh, the whole thing should be up and down. Okay, so.
As in like, if I had given you something like, say, sine of x plus 7, then you take the sine x picture and you shift it up 7. Does that make sense?
Yeah.
But if the sine x picture has not been shifted up, there's no number added on the end, it always starts at the origin. But yeah, all those transformations that we did with like parabolas and square root functions and e's and natural logs, they apply to this stuff too. If you add a number outside, it moves it up or down. Number inside will shift it left or right. But it is the case that I think when you deal with these things and stuff like physics, when you talk about things that oscillate, one thing that changes a lot is based on how long your oscillation is, the number inside with that x changes. So you got to know how to deal with that and get a sense for what the picture looks like with that there. Okay. -2 cosine of 3 over 2x. I gave you more grid lines here because it'll help us do it evenly. So first, what is the amplitude here? To find the period, you set 3 over 2x equal to 2 pi. Oh, so 3x will equal 4 pi, right? And x would equal 4 pi thirds. Eek. What to do with that? So when we usually graph a sine or cosine function, we take an interval, we divide it in half, and then in half again, which makes 4 or 5 endpoints. Does that make sense what I mean? Like there's the start point, and there's 1, 2, 3, 4, right? Okay, so this one, let's just count out. I gave you 7 for a reason. So there's 1, 2, 3, 4. Let's call that last one 4 pi thirds. What is half of 4 pi thirds? 2 pi thirds. So here's 2 pi thirds. What's this first tick mark right there? No, half of 2 thirds would be a third, yep. And then what's halfway between 2 thirds and 4 thirds? 3 thirds or pi. Do you see how what happened there is you're just counting by thirds? We got a third, 2 thirds, 3 thirds, 4 thirds. Here's 5 thirds, 6 thirds. Well, lovely. What would 6 thirds reduce to? I should have reduced it. 2 pi, yep. Okay. But this particular cosine function, it goes through its entire cycle by 4 pi thirds. So where would cosine usually start? Cosine usually starts at 1, right? But because this one has this -2 in front, where is cosine going to start? -2. Does that make sense? Because if you look at your unit circle, you say, okay, well, when I plug 0 into cosine of 0 is 1, right? I get this thing is 1 multiplied by -2 makes it -2. And then the basic cosine function, it usually does this kind of thing, right? It has the same point at beginning and end. So this one at 4 pi thirds is going to end at -2. When will this thing cross the x-axis? So that one crosses there and there, right? Pi thirds and pi. And by 2 pi thirds, you're up at 1. You've got to think about what happens to these 1, 2, 3, 4, 5 points on the cosine curve. And it goes like that. And then once you've got that basic pattern down, you can construct the rest. What's going to happen by 5 pi thirds? We'll be back at 0, yep. And by 2 pi, where's it going to be? Yep, it'll be up at 2. It'll be halfway through a cycle. So it went through 1 and a half cycles. And then could you get the rest of it on the other side? Where will your picture be at negative pi thirds? 0. Okay. By negative 2 pi thirds, you'll be up at 2, sorry. By negative pi, you're back at 0. 4 pi thirds, you'll be at -1. Negative 5 pi thirds, you're back at 0. And negative 2 pi, you're back at +1. When I taught this in my high school class, one of the textbooks called this the 5-point method for graphing sine and cosine, because once you have how long a cycle is, you divide it in half and then you half it again. Does that make sense? And then if you have a cosine curve, you start on the y-axis, right? If you've got a sine curve, you start at the origin, right? And then your cosine curve either goes from the top from the bottom to the top, or vice versa. So you got to just get the connection between these 5 points. If that had been a positive number, what would have been different? Which of those 5 points? Let's call them number 1, number 2, number 3, number 4, number 5. Which one? Where would this first point have gone if it was positive 2? Would have been positive 2, right? Would this point that was on the x-axis have changed? No. No. This point that's up top would now have been down below, right? Okay. And this point that was down below would have been up above, right? If it had been a sine curve, what would have been different? What if I would have, let's just graph this on there, what if I would have had -2 sine of 3 over 2x? Where would that have started? 0. What would it have done first? Go up or go down?
Down.
Go down because this negative. And then it would have been 0 again, right? And then it would go up. Do you see how that's also 1, 2, 3, 4, 5 points as well? Okay, so those 5 points get you one basic cycle of the graph, then you just kind of tessellate it. You copy paste it on both sides. And figuring out what that period is tells you where your one thing will end. See that pattern now? Okay, so that is the basic pattern. If you can get that much, you can graph the base of any sine or cosine function. Now we're going to do a little bit more with them today. We're also going to shift them around just a tad. So cosine of x minus pi halves. So when you graph something like, say, x minus 3 squared, how did that shift your parabola?
To the right.
Shifted it to the right 3. Does that make sense? So what this is going to do, this is going to shift y equals 2 cosine x to the right how much? Pi over 2. So I think it's probably smart to first graph 2 cosine of x. So we'll call that 2 pi, call that negative 2 pi. Where would cosine start?
Two.
Yeah, cosine is the x's, so in the unit circle, cosine is 1, the point is 0 degrees is the point 0, 1, 0. Cosine is the x. Cosine starts at 1, but then multiplies by 2 means it starts at 2.
Oh, cosine is the one's one, sine is the one that's.
Mm-hmm. Yep. Okay, by pi halves, by pi halves you cross. By pi you're at negative 1. Okay, so there's the basic cosine picture. So how are we going to shift that? To the right pi halves, and this is pi halves, right? So this point that's right there, we'll shift over to here. This point that's right here shifts over to there. Everybody goes over pi halves. And pi halves wasn't so bad because my curve was, as in my axes are ticked by pi halves. Does that make sense?
So does this kind of turn into a sine function?
This doesn't kind of, it does. Yeah. Do you guys see what he's saying? That shifting that cosine curve forward pi halves made it into a sine curve. And you can see from the pictures when you draw sine and cosine, they're the same shape, they're just shifted, right? Yeah, so this is the same thing as 2 sine of x. It's the exact same picture. Any problem that can be done using cosine can also usually also use sine somehow. But the whole point is the transformations you know from before also apply to this stuff. And when they give you weird pies, you're just going to have to guesstimate as best you can, like on this next one. I took this question from an Alex thing that I was looking up. Okay, so 1/2 sine of x plus pi thirds. So first, let's start by graphing 1/2 sine of x. So where does sine start? 0. And if this is 2 pi, and that's pi, here's pi halves, here's 3 pi halves. Okay. And since we said this has a 1/2 in front of it, what is the amplitude of this graph? 1/2. So if this is 1, we're not even going to get all the way up there. We're just going to get up to 1/2, back at 0, down to negative 1/2, back to 0. Okay. How are you going to shift this thing? Left or right? Left, and how much? Pi thirds. And I don't know about you, but I'm like, oh my gosh, how much is pi thirds? That are kind of like, I've got a bad concept of what that means. So if you think about in your unit circle, this angle is pi halves, right? Pi thirds is the same thing as 60 degrees. It's almost all the way to pi halves, right? Specifically, it's, I think it's 2/3 of the way. So you think about, 60 degrees out of 90 degrees. That is 2/3, right? So it's kind of like you shift this, if you think about that as 1/3, 2/3, you shift it over about exactly 2/3 back. See what I mean? It's a little bit harder to deal with, and that's why I don't like these as much, but Alex has a bunch of them on there, so you have to sort of figure this out. But if you divide all these things into thirds and use that will do the correct shifting. You shift it back 2/3. So that one moved there. This one goes back 1, 2, back 1, 2, 1, 2. Ugh, 1, 2. And I guess that is exactly what they intended, because this is pi 6, and this is 1626. Three, 6. See what I mean by that? Shifting by pi quarters is a little bit easier because pi quarters is halfway to pi fourths. Pi quarters is halfway to pi halves, right? Okay. But the basic idea of the transformations is the same. Okay, so far we've only combined the amplitude and a straight up shift. We haven't done the ones that go oscillate faster in a shift. Does that make sense? We're going to do one of those, okay? Because they are tricky and you got to know about what to do with them, but they don't come up quite as frequently. She's like, oh my gosh, what? So here's how you can deal with this. Write this as 3 sine of 2 parenthesis x plus. What you do is you have that 2x and something's been added to it. You've got to figure out, you've got to take out the greatest common factor of 2 and figure out how much is the shift. Because this 2 is going to be the part that determines how quickly your function oscillates. And you have to have it expressed as 2 times a quantity of stuff to figure out the shift correctly. So if I take out a 2, what happens to that pi halves? It becomes pi over 4. And so this means that your base function is 3 sine of 2x. And then that's the thing that you shift. I know that's weird. So if this were 2 pi, and this is pi, how many oscillations does sine of 2x go through in 2 pi? 2. So here's pi halves. Or you can say that 2x equals 2 pi, x equals pi. That's the length of one cycle. So pi, 0. So the sine function starts at 0. Is this one going to go up initially or go down initially?
Up.
And here, I've got an idea because I only gave you 2 tick marks there, right? Let's divide them in half, and we'll call this 1, call that 2, call that 3. So by pi quarters, you're up at 3. By pi halves, you're down at 0. By 3 pi quarters, you're at -3, and by pi, you're up at 0 again. And same pattern. Okay, so now that you have the basic function graphed, hopefully, what do you do to it? You shift it left or right, and you shift it left pi over 4. So shifting left pi over 4 puts the point that was on 2 pi just backwards 1/2 tick mark. Because the major tick marks that you drew in there were pi halves, right? And halfway to pi halves is 1/4. So everybody goes backwards pi quarters. So that one goes there, this one goes there. I think this makes it into a cosine curve, doesn't it?
So you can restate this as 3 pi cosine of x. I mean 3.
Let me look at it, okay, and then I'll tell you what you can restate it as, okay? I don't want to commit until I've actually had a chance to think about it. I think that you're right, though. I think you could state it as an unshifted cosine curve, yes. Yeah, this could be the same thing as 3 cosine of 2x, yes. It's the exact same thing. Okay, so those are definitely the most tricky. So just remember that you have to take out the greatest common factor to take out the leading coefficient of that x to figure out what the shift is. Your book has a different way to figure it out. I don't like their way as much. I think this is a better way to do it. And I think Alex also explains it this way, even though your book does it a different way. So, okay, and the very, very last thing, well, there are 2 things, but the last one, this one's we need to know. So we're going to find sine or cosine equations for curves that are given. I'm sorry these didn't copy all that well, but these were just screenshot off of Alex. So what I want you to be able to do is tell me, first of all, was this a sine or cosine curve? And then you've got to figure out what the equation for it is from there. And there could be more than one right answer, but let's stick to things that aren't shifted. So assuming that it hasn't been shifted, see how this curve starts at what is 5? And then by 2 pi thirds, it's completed 1 cycle, right? So which curve starts on the y-axis? Sine or cosine? Cosine. So this is a cosine curve. Okay. What is its amplitude? 5. So you know that you have 5 cosine of some number with the x, right? How do you know it's positive 5, by the way? Because it starts at 5. Had it started at -5, it would have been -5, right? Okay. So then the question is how do you do this? And you think about it this way. You think, okay, well, to find the period, you said, okay, b times x equals 2 pi, right? And that period was the x that came out, right? So if you say b times, what is the period of this particular function? 2 pi over 3 equals 2 pi. You'll figure out what that b is. Does that make sense what I'm saying? Okay, so it's gonna give you b times 2 pi equals 6 pi, or b will equal 3. So this is 5 cosine of 3x. That wasn't what I meant to do. I meant to do this. So the trickiest thing there is that number with the x, but the basic thing is that b times the period equal to 2 pi. So whereas before I find the period and I find the b, it's just the reversal of those two. Okay. How about this next one? Is it a sine or a cosine?
Sine.
It's a sine. Because you could make them all into cosines or sines by doing some kind of shifting of sorts, so we'll assume like this, the easiest way is a sine. What is its amplitude? 1. So far you know you have positive 1 sine of some number with the x, and the reason it's positive 1 is because that curve goes up initially. From the picture, what is the period of this function? Pi halves. So you have this equation, bx equals 2 pi. So b times pi over 2 will equal 2 pi. And you multiply by 2 and divide by pi, and you get b equals 4. So this is sine of 4x. Example 13 was just for fun. I'm not sure if I fixed this typo or not. Does yours have a sign in it, or did I forget it?
Yeah,
Did I put a sign there? Okay, good. This was actually in your textbook, and I thought it was kind of fun. They talked about Fairbanks. Like, legitimately, it was in your textbook. So the monthly average high temperatures in Fairbanks, Alaska are modeled by this sine model, where X is the time in months. And what this is saying is that, basically if you look at our temperatures, if time 0 is January, it kind of starts low-ish and it goes up. And there's variability, but it more or less does this like up-down oscillation pattern, right? So this will estimate what the sort of average temperature is on various days or various months. So I want to estimate the average high temperature on March 15th versus April 15th. So if x equals 1 is January 15th, what is March 15th? X equals 3. So then you just plug in 3. 0.523 times 3 minus 1.932. And I was just actually checking to see if they were accurate because I was curious. And the one thing you have to do is your calculator has to be in radians. So if you have a calculator, make sure that it's in the right mode. And when you plug that in, you get 23.92 degrees Fahrenheit. Does that seem like an approximately correct high temperature for March?
probably.
Yeah, I mean, it's on average, because March is the long month, right? And it is definitely colder in the beginning than at the end, right, as we observe this March. But I think 23 is probably a reasonable high. Wikipedia confirmed it. And April, it's a lot warmer, right? 37.4. What number plugs in for X there? 4. Okay, and that's approximately 43.16 degrees Fahrenheit. And this did model the average high temperature in April. So there's another function that models the average low temperature, and you can make another function that models the average, just average temperature, as in not high and low specifically. And does 43.6 seem like a reasonable thing for April? Like this week, the highs are all about 40-something on the forecast, so. Okay, isn't that kind of fun that Fairbanks was in the math book? Like a little bit? Yeah, all right.